probably share your screen.
Okay, share my tray. Not this one. Let me just go share. Stop sharing. Okay, before I start, can you see my presentation?
Yes, I can. Yeah, please go ahead.
Okay. So I thought, last week there were some questions. So I thought I'll just provide a few answers, although they are not very satisfactory answers, probably, but I tried to put something. One was about the porosity. I think it was asked whether autoclave cured laminates or resin infusion porosity, how do they compare? And it's very difficult because this void content, the porosity depend very much on the material and the process control parameters. I just put a few parameters affecting autoclave cure prepreg laminates like prepreg air bubbles, moisture content, volatiles, moisture in resin viscosity profile, fabric type, resin type, layup, thickness, layup and consolidations, type of part, curing process, parameters like vacuum pressure, temperature, hold times, and cooling rate, all these rates of increasing temperature. There are innumerable parameters which do influence the porosity. It's very difficult to outline what will really control the porosity level in a autoclaved or say vacuum. Vacuum, I have just put a few parameters on this slide. That's affected by fabric type, resin type, layup, binder type, thickness, that is number of plies in the preform, and of course ply thickness also. Preforming, how do you preform? What is the process of preforming? Part size and type. Resin infusion process parameters. Basically, there are lots of resin infusion parameters which influence the porosity. Curing parameter. So all these things do affect, and I sent this afternoon a paper, an article which is pretty big, long article. If somebody's interested in going through, had the patience, then one can read that article. It's interesting, but it's too detailed. Anyway, I can't go into the details of each of the parameters which influence that, but this is generalized. However, now coming back to the question of whether autoclave cured achieve higher porosity or RTM, again, it depends upon lots of parameters, but it is possible. And in fact, looking into some Haxel work, Haxel Composites work, and I found that they have been able to achieve the porosity level for the resin infused parts of about 0.5%. And this is again in the reference paper I sent from Haxel regarding that. So those who are interested, they can go through. Resin infused, the autoclave parts, normally, if it's well compacted and cured at 100 psi, normally one could achieve porosity level of less than 2% for laminates cured with autoclave, or it could be reduced further. But normally what happens in the prepreg, there could be some moisture, and when the prepregs are being laid up and being consolidated, there are always some volatiles between the layers could remain over the air. It becomes difficult to degas everything and remove all the volatiles in prepreg laminates. However, it's easier in the RI because resin can be degassed outside easily, and then the fabric preform can be remove all the volatiles, the air bubbles, they can be removed. So that way it is possible to get slightly better or lower porosity for the RTM parts. However, it's not always. If the resin injection process goes wrong, then you would have significant amount of porosity, and that is with everything. if the process parameters are not properly controlled, then porosity will exceed. Generally, for our allowables, we use as a baseline around 2% porosity for composite allowables, whether it's a prepreg or RI laminates. And beyond 2%, if the porosity level is higher in a part, we need to generate the knockdown factors, and I'll discuss about that later on. So it's an important thing, porosity, because increase in porosity does degrade, especially the compressive strength and the shear. RTM was a lot of, I just, put some chart from Haxel paper to compare the laminate prepared using autoclave, using a prepreg tape and also water. And generally what happens, what has been seen, that compressive strength slightly reduces. And I have explained that compressive strength is usually the function of fiber volume fraction and the matrix modulus in general. So compressive strength increases with the increase in VF. Compressive strength increases with increase in matrix shear modulus. So higher the modulus, shear modulus, higher the compressive strength, until it reaches a plasticity stage where it becomes nonlinear behavior. And generally the RI fabric, when you buy the fabric, which has the binder, or it could have a thermoplastic nylon film bonded with it, usually the action due to a binder or the film may act to reduce the shear modulus because it may soften the laminate, may affect the fiber matrix interface. Therefore, VF is not the only reason to reduce the compressive strength for the high type laminate compared to prepreg. There are other reasons also. And I just copied some of the data I replotted from that paper to make it better. So what this chart shows, it is the ratio of the property for the prepreg versus RI. So it's the ratio what you see here. If it's 1, they are equal. If more than 1, that means prepreg property is better than RI. If it's less than 1, then prepreg is lower. Oh, is it? This seems to be. I'm sorry, this is UNC. Let me just look into the original paper. Did I put the data wrongly? Just excuse me for a while. Sorry for that. Oh, come on. Materials, RTM process, item SMP. Okay, that figure is correct. Now this one, in fact, prepreg is lower in compression. However, there's a case where the prepreg value is higher, but it depends upon the cases. So in this case, for this material, this is correct, what you're seeing on the, according to that paper, published paper. So I think this is wrong. I'll have to look into really why I put this statement. So I'll just go into, sorry for that. If there is any error, I'll correct it. Now, there was another question about RI processing of phenolic resin laminates. And of course, I don't have any experience of the phenolic resin. I think that was a question. the person who asked the question, phenolic resin?
I think that person is not around, right?
Okay,
yeah, so maybe you can go ahead.
So
We'll
so I don't have any experience, and naturally, what happens for RTM, like RTM 6 resin or RTM epoxy resins, normally from Cytec or Hexel, they are pretty good and controlled parameters, injection parameters give reasonably good look, good laminate and long parts. In fact, you can make using the resins from Hexel, but phenolic, I don't have it. So, okay, then one can always refer to Hexel composite, liquid molding composites from Hexel, the guidelines and the processing. And of course, as I said last week, NAL is the most experienced. They are the expert in resin infusion process. So they know most of the details. Okay, now, are there any questions from the last lecture or from this discussion before I go to the main lecture? Okay, if there's no question, then I'll just skip and I can start. Stop sharing, open tray. Okay, this is my main lecture, and I think it has been going pretty slow. I want to material screening. I think we were last time material screening. I think I was discuss this. Anybody remembers?
I think you were on slide 135, if I remember right.
Okay, so material screening. I think I started discussing about this material screening and selection. So the purpose of material screening and selection is evaluation of various materials. When you're launching a new project, new material has to be selected, suppose for the process. If material is already available, of course, you don't have to consider this. There will be materials that are liable. So, but say when I give the example of 787, this empty surfaces, which was using the new process like resin fusion process, and the company didn't have any materials qualified for that system. So naturally, the new materials have to be found or sourced from the various manufacturers and see which one is the best and develop all the material alliables, material qualification, material alliables, everything together, which I'll be going through this game. So, and that's at least the advantage now we have that we started right from the scratch in this program for the process and the materials. And we built up the alliables and design values. So, and of course, when you are screening the material, you have to use the information from the supplier, manufacturer, or if there's some literature that are available, company experience, and then test the materials, evaluate them for various physical, mechanical, and chemical properties. So now materials screening and the final selection for this resin transfer molding process or RI. So you have the fibers, fabrics, binders, resins. And evaluation was based on manufacturer data, past experience, physical test, mechanical test, micro-cracking evaluation, and test at various environments and effect of various fruits. So significant amount of testing was undertaken for quite a few materials we had tested, in fact, evaluated various type of fabrics, fibers, the binder types, the resins, and then finally what was used, the final selection of the material based on the evaluation. And it's an intensive process, in fact, because if you go wrong in selection of materials, then the whole of the program is affected. So one has to be very careful in selecting the type of the material which the program is going to use. Okay, properties for evaluation. They are quite general properties. Of course, fibers, tensile strength, modulus, elongation at break, fiber diameter and density, economics, fabric, aerial weight, weave, drippability, fabric tau, cost. Screen test binder material. Binder provides the bonding to dry fabric for preforming and may also enhance interlaminate fracture toughness. So evaluation includes fabric adhesion characteristics, glass tension, temperature, processability, density, aerial weight of binder film, effect on fiber matrix interface due to binder, effect of binder on microcracking. So one has to assess that due to the binder, other properties are not affected to the detrimental side. Screening test resin uncured, shelf and pot life, gel time at various temperatures, viscosity profiles. In fact, one of the most important things about the resins for RTM is the viscosity profile. Cure cycle, resin density, ease of processing, that is injectability. So all these parameters were evaluated, and then final resin was selected. Resin cured, density, tensile and compressive strength, modulus, fracture toughness, moisture sensitivity, adhesion with fibers, glass tension, temperature, dry and wet, material operating temperature limits, thermal coefficient expansion, chemical shrinkage at cure, coefficient of moisture expansion. So all these properties, various properties were evaluated. Effect of fluids for evaluation. So this is also very important when you are evaluating the materials, that you don't want the degradation of those materials due to the aviation fuels like jet fuel, lubricating oil, hydraulic fluids, de-icing fluid, MEK washing liquids, clean solvent, isopropyl de-icing agent, water. And we did test various materials for the effect of these various liquids or fluids. So we have to assess the sensitivity of the material due to various fluids. Conway, this is another thing, mechanical tests like for the evaluation of the fluids, normally we consider the matrix dominated properties. So like a open hole compression and 45 plus minus 45 for shear modulus and strength. These are the typical coupons used in order to evaluate the effect of fluids. Normally fiber is not affected, so that's why we concentrate our attention toward the matrix dependent properties to reduce the test matrix. Physical tests like fluid absorption, weight gain, microscopic examination for any microcracking. Just shown schematically various coupons like unnudged compression, tension, open hole compression, open hole tension, and compression after impact. I won't go into the details of these. Cured laminate physical properties like a fiber volume fraction, voids, porosity, density, glass tension, temperature for the material, laminate thickness variations, moisture absorption behavior, laminate hygrothermal cycling for microcracking investigations. Now, here I just emphasize on this one. Next slide, I'll show. What this is showing, and this is an important characteristic to be evaluated for a material, that due to the hygrothermal cycling, the cracking should not occur. A systemic cracking should not happen in the material, otherwise the material is not suitable. The micro crackings due to the environment is not acceptable to the company. So in order to assess the hygrothermal micro cracking, one of the tests is, this I have taken from NASA report, that you will have the small coupons and then you will heat it up, exposed to the humidity control chamber, and then you will cycle thermal cycling Tmax. I have not put the temperatures, like normally whatever the temperature is decided depend upon your operating temperature environments. So they will dictate the cycling temperatures. So what happens after cycling to some number of cycles, like 100 cycles or 500 cycles, you will cut the coupon and see if there is any micro cracking, like I've shown on the right, microscopic examination of the coupon. And you will repeat this, like suppose 500 cycles, then 1,000 cycles, then 1,500 cycles, 2,000 cycles, 2,500 cycles, like that. 4 or 5, you will consider, okay, my 2,500 cycles or 3,000 cycles will cover my lifetime. So you will keep on cutting at the intervals these coupons and examine to see systemic micro cracking. If it occurs, then that material is not acceptable. I've just written some notes over here, Tmax, Tmin. I won't go into the details of this. Okay. Now, block 2. Any questions so far on this material screening? No? Has anybody been involved in any testing, or is all new? Okay. Now, materials and process specifications. Now, what is the importance of this one? Why do you own this? Basically, material and process specifications are done to control the purchase of critical materials, because when you want to purchase the materials, once you have decided the material, then you want to purchase the material. And so you have to qualify the material. You have to develop the process specifications so that you provide, based on the process specifications, material and process specifications, you provide the information to the supplier so that the supplier can supply the material meeting your specifications. So it's very important to provide the specifications to the supplier so that the material supplier supplies the material, which has to conform to your requirements. So in order to generate that, you have to yourself test the material and then develop the material processes, material specifications and process specifications. So essentially, this is to control the purchase of critical materials, to assure that the material does not change substantially with time, to establish acceptance, equivalence, and quality control values. What does it mean? That, okay, you have given the material specifications to the supplier, and supplier tests the material before it ships, and according to your requirements, and supplies the materials to you with a conformance report. However, as an accepting organization, we would also test a few coupons just to make sure that it meets the specifications. That is called acceptance testing, which is done by the industry or the user. Okay, specification values are statistically based derived using Main Book 17 procedure. Again, they are the same type coupons. I won't go into the details of this. Physical test, similar to what I showed in the material selection, similar type of test. Material specification, data analysis. So now data analysis, of course, this I've just, one can use the Main Book 17 as the method is from the saddle method proposed by Mark Wengel. He was a statistician and he has written a lot of work. Analysis methods and also Main Book 17, his major contribution is in Main Book 17 methods to estimate the variables. Okay, now this method is, of course, you may not be needing this. However, I just want to give you the method. What it says, the minimum maximum averages and the minimum and maximum individual values for that, whether it's a stiffness or a strength, are given by these values like mu minus K1 sigma, the K1, K2, K3, K1, K2, they are the parameters based on some tables given in that paper. Don't bother about it. So mu and sigma are mean and standard deviations respectively, K1, K2, extremum parameters. I won't go into the details. So based on this, your data, you test like 6 batches of the material, like 30 coupons, like tension will be 30 coupons, compression will be 30 coupons, and so on. And then you analyze the data. You develop based on that method, minimum individual, minimum, because this is a statistical process. So based on that, you calculate and then provide the table like minimum individual value like E1, E2 suppose, and say strength, minimum individual, minimum average, minimum individual, minimum maximum, sorry, minimum average, maximum individual, maximum average. You provide this table, develop this information, and then this information is provided to the material supplier who has to meet the material before he supplies, meet the requirement, whatever is in your table. And then you have to repeat yourself to verify whether the values are correct or not, whether the material which supplier has supplied to you is satisfactory or meets the requirement. Anyway. Arrivals and design values. Now, this is important. After you have done the material specification, material is received, now you want to develop the arrival because these are the values which you want to use in the design, not the values developed over here because the analysis type is different over here than here. They are the firm material arrivals for the design you develop using the statistical process. You consider the effect on environment, effect of notches, joints, radius, and other design features, effect of ply orientations, percentage, stack sequence, laminate thickness, hole diameters, sensitivity of fabrication process, that is cure conditions. It's important. You determine the effect of, say, like curing temperature, the rate of cooling, rate of heating, the whole time at the cure cycle, so many parameters which have to be evaluated because you have one process parameter, that is your baseline parameter, which you'll be using in production, say. However, quite often one may find autoclave goes wrong or some pressure failure is occurring or rate of cooling or rate of heating failure occurs. For all those anomalies, you have to prepare the data, which I'll be discussing over here. Effect of fabrication anomalies. What is fabrication anomalies during production? there could be some failure of process, or when they are drilling the hole, holes could be enlarged, or some fire breakout. I'll just consider that those who are interested. Effect or repairs. All these parametric facts have to be studied during the IISc program. It becomes a pretty big program. What is allowable when we are talking? Allowables per AC 2107B is defined as lamina and laminates test data on a probability basis. You determine the allowable based on A basis or B basis. I'll explain what is A basis and B basis. Design values, again, a material property or load value that takes into consideration program requirements, fitting and scaling factors, cutoff levels. Determinant of test data and chosen to minimize the probability of structural failures due to material variability. The main purpose of design values and allowable says that you want to account for any variations in the process, the material's variability, and you do not want the structural failure to occur because of the variations which may occur. So yeah, right at the time of allowables, when you're determining, you will consider these variations and determine the allowable property. What is A basis and B basis? A basis is defined as statistically based material property. That is 90% of the values in the population will lie above A basis value, 90%, 95 with 95% confidence. What it says, suppose you have 100 coupons tested, and out of 100 coupons, whatever values they are giving, the 99% of the values in the population would be higher than the design value which you have specified. And what is B basis? Same thing. Instead of 99%, now only 90% of the values will be higher than the B basis value. Now one would ask, okay, there's a 10% chance of failure then. Yes, the probability of failure is there, 10%. However, what happens, we have some other safety mechanisms over here. We use these B basis values for the structures we have multi-load path. That is, one load path may fail, then other load paths may take care of it. This is where we use B basis. A basis is used when the structure is having a single load path structure. That is, only one load path. If it fails, the structure will catastrophically. That's where A basis is used. Now, I just showed schematically a chart over here. This is hypothetical data that what is A basis and B basis. You see, A basis is this, where, oh, sorry, A basis is red one, sorry, I'm sorry. A basis is this, where almost every data value is above this line. So that means there's significant safety involved in it. With B basis, there may be some data which may be lying below. I've not shown that, but there may be possibility 10% data could be below this line. So that's the difference between A basis and B basis. Criteria for test matrix developers. Okay, now, what is the basis of developing a test matrix when we are developing for a allowables program? First thing is, one is the basic Ply data which we require in order to generate the allowables, like unnotched tension, unnotched compression, Ply Modulus, and strain to failure. They are the basic. Then we determine notched strength allowable based on a quarter-inch hole, open hole compression, open hole tension, filled hole tension, filled hole compression. Compression after impact, we'll have some coupons, we'll impact them and test after impact under compression to determine the residual strength after compression, after impact, sorry. Special features, you have lots of joints in the structure, you may have holes, notches, you have to test those features. You'll have radiuses, you have to test those radiuses, design layup envelopes, geometric parameters, environments, loading condition, certification requirement. So all these parameters are considered in order to generate the test matrix, which would run into hundreds and hundreds of coupons. Schematically, I've shown certain Ply properties when you want to determine for the levels, 0 degree tension, 90 degree tension, 0 degree compression, 90 degree compression, in plane shear. For many of you, I think this must be very new. You may not have dealt with the testing, but however, it could be useful to provide you some background that what industry would need, or during your, suppose you are doing PhD or masters and you want to develop some test matrices and consider some tests for coupons, this could be useful information for you. Okay, now properties here, we develop modulus, Poisson's ratio, failure strain, failure stress. We test multiple batches. The reason why multiple batches of materials are tested, just to show, or just to see if there is any variation between one batch of material to another batch of material. And it's important to get a better statistical value, because it's possible when, say, Hexel is producing the material, one batch, another batch, it may not be exactly same. There are always some differences, possibly. And that is why we need to test various batches. Normally, the recommendation is 6 batches of the materials from the supplier is tested. So for a good B basis, 6 into 5, 5 coupons for each set, 6 into 5, 30 coupons. Test conditions, you have to test various environment like cold condition. Cold temperature could be -65 or -55 centigrade, or hot temperature like 70 degrees centigrade, or if you're working with a fighter aircraft, which operational temperatures may be higher, need to be tested at 80, 90, depending upon your requirements, you would consider hot, cold, and also the wet. It's important because effect of moisture is very important in composites. The matrix properties get degraded substantially with the moisture and temperature. So it's important to consider STW. Output, average Ply modulus and Poisson's ratio, compression, tension, and shear. No statistical analysis to perform the modulus. Only the statistical based values are the strengths. Metal alloy stress, the other like unlost tension, compression. I won't go into the details of this. You can read actually the various tests which we need, and material parameters, layup, diameter, various thicknesses, and fastener pitch and all that. So I'll just skip this. Now, how do you define the Ply modulus? Because if it's a nonlinear behavior slightly, and usually, of course, fiber-dominated laminates will behave quite linear. However, if it's matrix-dominated, it would have nonlinear. When we are defining a Ply modulus, it's generally defined as secant modulus or a chord modulus. There are two definitions. Now, secant modulus is defined. Suppose secant modulus, a particular design strain value is defined. ES4, secant modulus, S4. So this is stress divided by strain gives you the secant modulus. Now chord modulus is between two strain values. So chord modulus between E1 and E2 will be defined as S4 minus S1 divided by E4 minus E1. So it's a matter of choice by the organization, what they choose to define for allowables. Generally, I think secant modulus could be preferable. And in order to choose a particular value of a strain, normally this strain value at which you will define the secant modulus is chosen for the design value, nominal design. So strain value chosen for modulus calculus depend on organization, whether it's a secant or chord modulus. Modulus should be calculated in linear region of the stress strain curves. Now, analysis strain data analysis, data set from multiple batches, statistical analysis, A basis or B basis. And here the analysis using same Mill Handbook 17. What happens when you have tested the coupons for a baseline parameter, you will do the statistical analysis for that baseline, like we design baseline, I've said, and then the parametric effect. Suppose you have determined for nominal thickness laminate the compressive strength, and then you are varying the thickness, you are varying the diameter of the hole, you are varying the layup percentage of 0° fiber. So what happens, all those parameters you will try to compile as the effect of that parameter on the baseline strength. And that is why I've just said, okay, this is my baseline strength, and these are parameters affecting the strength C1, C2, C3. So baseline CI's parametric effects such as environment, thickness, layup, load types, diameter, width, all these are compiled together, and each one effect is applied. You plot the charts of each one and then generate the equations so that they're easy to apply in design. And that is how you generate allowables and parametric effect. Just schematically, I've just shown some graphs. Suppose this is notched strain value tension with percentage 0° fiber in laminate decreases. Environment, as the temperature goes up, the value comes down. Thickness, when the thickness goes up, it just remains flat. Initially, it rises, and diameter, as the diameter goes up, usually our strengths will come down. So just schematically, I've tried to show these parameters, and the test data is generated for all these parameters and equations, normally empirical equations generated. Okay, laminate physical test. This is similar to what I showed in the materials screening test, like properties, fiber volume fraction, void content, all this. Again, it's a repeat. I won't go into the details of this. The other thing is impact damage survey. It's important because we would like to study the effect of various impact energies on the damages generated on the laminates structures, depending upon thickness, layups, and we just want to have a feel. So some representative boxes will be made, and you would impact the laminates, different thicknesses over the ribs, spars, away from the ribs and spars, and determine dent, energy level, and the damage created, and develop the relationship between the impact energy, damage detectability, and the damage characteristics. Just schematically, I've shown impact at various energy levels and laminate thickness. So you may have a different, in a box, you make a box and T1, T2, different thicknesses and different ribs, and apply the impacts, determine the energy required for each of the region, and then develop some relations between the damage and the energy. Impact damage survey, configured structures continued. Post-impact evaluation can reveal the purpose of all that is damage visibility, extent of damage like laminate cracking, fasteners and hole damage, substructure damage like ribs, spars when you are impacting this is a rib and you are impacting over here. Now what happens, sometimes you may not see any damage over there, but there could be substantial damage to the rib. Radius may crack. And that is why it's important to understand the behavior of various impacts on the structures in composite. For metals, it's not important. Metals, it doesn't happen. It's only in composites. Fastener hole damage, substructure damage, rib spar stiffness, reduced local stiffness, loss of load path, residual strength, relationship between impact energy, damage trajectory, and damage characteristics. Okay. This graph shows the impact energy versus limited thickness. For the same damage to be created, like a 0.127 millimeter dent, yes, you would realize as the thickness goes up, you would require higher energy. Same thing for this 1.602 millimeter dent, 1 millimeter dent nominally. Again, as the impact energy increases, for the laminate thickness increases, impact energy will also increase to create the same amount of damage. So this is just, I won't go into the details of that. Structural element test. Now, previously we considered in block 3 the reliables, the basic reliables, which would be applicable towards all different structures. However, now there may be your structural features may be different from another structure. So naturally, looking at your structural features, you may have to do some special tests besides those basic reliables. And this is what it is here. So structural element test, design values that are related to structural features. What are structural features like bonded joints or bolted joints, the radius, and there could be some other features which you need to evaluate. Effects of manufacturing induced anomalies. During manufacture, there could be like a fire breakout. I'll explain actually what a fire breakout or enlarged holes, the wrong countersink, sensitivity to fabrication process changes, and effect of repairs and service. Okay. Just schematically, I put some pictures here to demonstrate. So typical structural features. Suppose this is a structure. We have joints and some damage to the impact. There's a hole, a notch. So these are various features you need to investigate. And these are ribs, skin, joints and tensions. So what happens, suppose this is a joint and you have a pressure. So there's a pressure and there's a in-plane force also on this. So like that, you have a laminate joint, bolted joints. So it's in-plane load and also the out-plane load. And trailing edge joints, the various joints are very critical in our structural design, and we have to be utmost careful in considering joint strength and geometries. They're trailing edge joint, and these are double countersink rivets, and in some structure they could be heavily loaded. And somehow, what happens, these double countersink fasteners are not great. And there could be significant problem about these trailing edge fasteners, and the design becomes critical over here. So trailing edge joints are complex to design. Various issues are fastener type, trailing edge skin design, joint gaps, joint sealant, installation, loading types, the repairs. So these double countersink rivets, they become critical joints. Then I think I mentioned last time in last lecture, some of the features like you have the rib, you have this pressure. Of course, fastener goes in plane load and also under pressure. So it's a pressure on the outer plane load, in plane load. That's one thing. Then what happens to this load? The load has to track through the radius. And as I said last time, the laminates, in metals, this is not a problem, high strength material. In composite, because there's a load, this load, it creates a bending moment over here. And this bending moment creates opening bending moment. An opening bending moment will create the tensile stresses as an interlaminar stress. And since the composites are weak, and through the thickness property, the failure is likely to occur. So we have to test lots of radiuses and design it so that the radius failures do not occur. Usually, these ribs are designed by this. It dictates the design, thickness, and the layups. Hello, any question? Okay. Now, other structural features are there are lots of joints, especially with the fittings. Suppose you have a nested fitting. This is hinge and actuator, and this is attached to the structure through the fasteners. This is spar, is skin. So load from the fitting has to be traveling to the structure, and then these fasteners have to share significant amount of load. One has to be careful in designing these joints, especially our experience has been that this joint is very critical in fatigue loading, and usually the fatigue will design the criticality of these joints. Okay, and now one of the problem with this is when you are doing this design of these joints, which is say laminate composite, another laminate, this is a metal, and there could be some other shims. Shims normally degrade. This also acts like shim. Load directly transfer from here, metal fitting to the skin mainly. Spar picks up only very little load. So basically the bending moment is high on these fasteners. And you have to consider, usually we have to design based on the test data, because it's extremely difficult to predict theoretically the fatigue behavior of the joints. Usually the process is you test quite a few joints in fatigue, static, and develop some kind of empirical methods so that method or the data can be applied, because you can't test each of the configuration, each of the thickness, the shims and all that. So you test only a few representative ones, and based on that, you try to cover your design envelope for the structures. Any master's student can try to see if they can develop some kind of a procedure to predict the fatigue life of the metal to composite joint. It's good work. Any questions so far? I think everybody is very quiet.
Sir, just one question, sir.
Yeah. No question.
Is this fatigue life means it's difficult to decide because because of the preload relaxation which is happening or something like that? Because because the fasteners when we preload for CFRP they undergo relaxation, right? The preload will be relaxing over time. Is it because of that?
Well, it's not only because of that. Of course, we design say static joint strength when we determine. We design the static strength assuming that there will be relaxation or 50% relaxation would occur over time. So we understand that. In fatigue, what happens? Due to the fatigue cycle, when the fatigue cycling is occurring, the frictions may be affected. So fasteners may start rotating if it's not properly clamped joint. Or there are many members like shim, usually soft shim, it degrades the joint. So after some time, it may start rotating the fastener. Once the fasteners start rotating, that's the end of life. And that is why these joints become very critical. We evaluate based on the testing. So during our program, we tested lots of different joints to evaluate them for the fatigue. I said very important. I would always emphasize in any design, they start with the joints. And even John Hartsmith, who has been the basically expert on the joints, you can find in any composite books, papers, John Hartsmith's papers on the bolted joint, adhesive joint. His philosophy is also start with the joint.
Okay, sir. Okay. And sir, while evaluating that A basis properties, we are considering the batch variation as you told, like 6 batches, 5 loads each. And now for the acceptance of subsequent batches, is the property compared versus the already established A basis or B basis?
It should be because that is what you have considered normally. There should not be more variations occurring.
Okay, and our
do not expect the supplier of the material to vary in properties.
Okay, sir. Okay.
We control it, as I said in my that the material specifications. They manufacture the material as per the specifications, and then they have to meet the conformance requirement. They have to provide a conformance certificate, and the industry, when the industry receives the material, they make a few tests to see whether the material which comes in-house meets the requirement. If it's not, then the material may be rejected or accepted with the non-conformance issues to see whether it's acceptable or not. So there's always a very strict check, quality control for the material received inspections, material received. So your question, there could be variations due to the batch. Of course, you assume that the batches which you have tested would have already considered various scenarios.
Okay, sir. Okay, fine. Thank you.
Normally, we don't find, and of course, what happens once you have decided about alliables, you are not testing the materials for those alliables every time. No, they are logged in, and you would assume that material alliables are mapped by the material which you are using. You don't keep on testing. It's only the acceptance test. That's only a few tests, not that heaps of data is tested.
Oh, okay, fine, sir.
Like there may be about a dozen coupons for compression, tension, that's it. For the receiving inspection or some interlaminar shear, that's it. Alliables are always logged in, you don't change them.
Okay, sir, fine.
Any other question?
Sir, I would like to ask one. The joint which is shown on the current slide, like it's if there is a skin in blue color, then this is a spar in green color, and I think this is a metallic part which is sitting inside the spar.
Yeah, so this is metal. Yeah.
Yeah. So it's really a complicated joint, and I think these are the fasteners. Those.
These are fasteners. Yes.
Right. So for such a complicated joint also, would you not consider, the bonding also maybe of the spar with the skin?
That's another topic. Bonding.
Yes, I mean,
Well, there are a lot of issues with that. And if I want to discuss that,
okay.
that could be a separate thing. In fact, as you know, NAL, that's the wing box they made demonstrator, where they have unitized the spars, ribs, everything co-cured together.
Okay.
So that's another philosophy. Of course, then what happens in that case, you can bond or co-cure one of the skins with a stiffener or spars, but other skin has to be bolted. The issue with the solution is not very simple. It looks very simple. Okay, we can always bond this with the skin. Bonding is not reliable. And especially for the critical structure, I would not like to have the structure bonded and carrying such high loads. No, we won't accept it. So it depends. There are a lot of ways, a lot of work is being done around the world for integrally co-cured structures. But there are many issues. It's not that simple. In fact, I had prepared one presentation for ADA when they wanted me to assess the co-cured co-bonding and the bolted structure just to study the effects. So that's another topic. I can talk about it, but currently I don't have this out of time. But it's a good question. Yes.
Yeah. Thank you, sir.
Joints are more reliable than adhesive bonding.
Okay. I think for adhesive joints, qualification becomes very difficult. The glue line thickness, its maintenance, and
it is. There are lots of issues with that. It's not that it's not being done, but for the critical structure like the spar, currently, I would try to avoid.
Okay. Fine, sir. Thank you.
You're welcome. Good question.
Yeah.
Various possible element tests. So various elements like fastener, single shear bearing, two fastener single shear bearing, fastener pull through, radius interlaminar fracture test, laminate buckling and crippling test, shear tension interaction for fasteners, in-plane compression with BVID in panels, notches and holes in laminates, tension compression, fracture toughness, repair validation of many. So various tests actually, I would like to devote much of the time. Some of the coupons, representative coupons I've shown here, like a single fastener bearing test when you're doing to make the stabilized coupon. It like ASTM standard fixture for bearing test. Again, fastener pull-through test. You want to study when fastener tension load is there, whether it will pull through the laminate or damage to hole. What happens is important because, as I showed, suppose rib to skin joint, under pressure, the skin will try to lift. It will create a tension load. Say in this scenario, it will create tension load in addition to bearing load, the in-plane load, and then it is possible the fastener may pull through. So when we are designing the structure, we have to consider each and every mode. What is possible to fail this and validate it. You cannot allow any failure anywhere. And the just representative coupon I have shown because there's a tension loading as well as the bearing, so some kind of interaction. Various type of tests could be done. Coupon file event for BVID, notches, holes of notches. Again, I can't go into the details of these. two-way crack, damage for damage tolerance, static, and tension compression. Repair test validations. So you have to, when the product is being sold to airlines, naturally the manufacturer has to provide the repair manual. In order to provide the repair manuals, that means for various repairs which we are suggesting to the airlines, the repairs have to be validated. We have to work out the strength of each repair, structural integrity of the repairs, and then put in the repair manual so that the airlines can repair when the damage occurs. And there could be larger damages which airlines can't handle, then they would send it to the manufacturer or some big repair depots for the airlines. So suppose we consider scarf repair, then we'll do the analysis, scarf analysis strength using FAM, analytical, fracture analysis, VCCT or analytical, and verify your analysis methods by using the coupons, elements, subcomponent, components. Repair issues, manufacturer and in-service repairs, repair material different to pristine material. What I'm saying, one of the problems with the RI laminates is the repair method when you want to use, you can't use the RTM method or RI resin infusion method for the repair. That means your pristine material has been prepared using the resin infusion with, but the repair material can't be resin infused. That has to be pre-pack. Now, when you are trying to use the pre-pack, there could be mismatch in the ply thickness, and there could be mismatch in the material. It could create some difficulties. Additive material repair and pristine material ply compatibility, scarf, taper, that is taper ratio, surface ply and overlay ply, inherent flaw considerations. So various parameters have to be considered. Hard point effect, repair size limitations, repair damage tolerance, repair fatigue, failed repair conditions, repair validation method, when we are saying repair failed condition. One of the requirements for the repairs is that we have to assume during service, if the airline has done some repair, permanent repair even, using a process, but still there is a chance of repair failing. So we have to provide the design strength when the repair fails. There's a requirement, a damage tolerance requirement for the repair. It's mandatory. And the repair validation methods, of course. Production anomalies. What are these production anomalies? He said, when the fabrication is done, assembly in the air car assembly line, there could always be some defects. Some tool may drop, the drill may go wrong, the laminate may have some depression due to the cure cycle failure or something. There could be higher porosity than the nominal porosity. Favorable infections could be higher or lower. Filled hole repairs, countersink depth variations. There could be wrinkles. When the layup is done, after curing, the laminate may have wrinkles. Especially wrinkles happen near the curvature. And this happens to be a significant part of the process development, because quite often in the beginning, when you are working with the laminates, the process development, I can tell you a lot of wrinkles happen, and then wrinkles are not acceptable because they may degrade the strength and stiffness. we had to spend significant amount of resources in order to qualify for the wrinkles. That happens with any material. So one has to work out the allowables, knockdown factors for the wrinkles, and they would always occur in practice sometimes. Off-axis drilled holes, fiber breakouts at hole edges. I'll just show you in the next sketch, actually, a couple of sketches I made. Delaminations around holes, cure conditions, cooling and heating rates, cure time, and temperature variations extended. So various parameters which may affect. Here I've just shown some schematic diagrams, just say wrinkles. So there could be out these wrinkles, the way the plies deform, so and cause wrinkles. It causes the strength degradation. There could be internal wrinkles, surface depressions. Then the mist drill, when the holes are being drilled, the drill may hit a wrong spot. So it's a mist drill. Countersink, deep countersink. When the holes are being drilled, hole becomes deeper. Tilted countersink, when the drill is there, it may tilt. So these are, and then delamination around hole edges, delamination response, then fire breakout. When the holes are being drilled, normally what happens at the exit, the drill is coming out, it may take away ply. So this fire breakout, like I've shown here. Then sometimes there could be, when they're trimming the edges, there could be fire breakout over here. One ply comes out. Nicks or gouges or scratches, there could be some tool drop or somebody puts a scratch, so there could be some nicks or gouges. As delaminations. All these various defects which may occur in production have to be accounted for during our design so that the engineers, quality engineers, they know what defect is acceptable and what is not. And that is why we need the parametric estimations of each of these various defects which may be happening in the practice. I won't go into the details of this data analysis qualitative method. Okay, I'll just show you some of the test coupons or tests. This is just a crippling test which comes from that publication. It's just typical coupon channel section to determine the crippling behavior of the material. This coupon shows some of the repair tests, repair coupons as a picture from shear. We had, say this is a repair. And then when we pulled it in tension, it applies a shear loading, that is compression on this, and tension along this line. And you can see the failure. So it is a pristine laminate and repair laminate. So lots of testing we had to do for various types of coupons in order to generate the allowables for the repairs. Won't go into the details of this again. Here is another coupon which I'm showing you for large panels. Of course, this is not the only one. We tested very big holes, small holes, big holes in large panels. So large panel tested to determine residual strength to various laminates with holes and notches and BVID in tension compression. Test include the holes and notches of various diameters and laminate types, static and fatigue test. Okay, now durability testing, which is normally the fatigue testing. Environmental testing, hydrothermal coupons nominal with resin-rich areas in plane, laminates, and the radius, effect of cleaning jet flows. So that's a environmental testing, mechanical testing, coupon fatigue, element fatigue, subcomponent fatigue, component fatigue, sonic fatigue. So various fatigue coupons we had tested in order to demonstrate the durability. Possible coupons element test for durability, open hole fatigue test with various holes and layups, stress ratios. BVID fatigue coupons, that is barely visible impact damage. You will impact the coupon and then test in fatigue. Bearing and fastener fatigue coupons with fastener thicknesses and so on. Shims, stiffened box fatigue, shear tension interaction fatigue, radius fatigue test, fastener pull-through fatigue test for coupons with production anomalies, repaired fatigue coupons. So that was subcomponent test. Now how much? I think there's not many yet. So what I'll do, I might stop here and take the subcomponent test next time. In the meantime, I've got 10 minutes still. I would like to answer the questions if you have any. Any questions for today's or previous lectures?
Sir, I would like to ask one.
Yes, please carry on.
This repair also we characterize it, but during repair we have to machine the composite first, maybe by milling or something like that, to clean up the damaged area. So the damage because of machine, do we also characterize and include in the certification, or I mean, how do we go about this?
Say, let me just. You have this pristine laminate and there's a damage over here, say, for example.
Right.
So what you will do when you're trying to repair the damage has to be cleaned up and create a scarf, because we normally would define the scarf ratio of 1:30 or 1:50. Normally 1:50 is very thin laminate, 1:30 is typical. This scarf ratio is nothing but this divided by this angle basically.
Yeah.
So you have to machine or sand it basically using sanding to achieve that. And then of course you are doing the repair, putting the plies. This ply when it's coming is coming here, the ply will come here. It's not really representing the way the plies are laid up. It shows but joined, but it's not like but this ply. I think schematically I should be having a let me think. I think I showed last time, but let me just see. Should we add lectures, question answers? Just looking at. Okay, let me just open the tray. I think I showed this slide last time, like when you have done the scarfing. Can you see this slide?
Yes, yes.
Okay. And then what happens when you're trying to lay up? So the first ply with the adhesive over here, fully bonded, so it interfaces to some material and then next ply. So like that, you would repair, and then finally you would have some overlay ply. So there are methods of these repairs, scarf repairs, and this is like what you were saying, machine. We call say sanding, so machining the surface and then cleaning it, putting the adhesive, then putting the plies. This is our process. So is that your question or?
Yeah. So what I wanted to ask, the qualification of the machine surface. I mean, typically what will happen? Some may have only the milling. They may only mill, but some people may sand it also after milling. So do you also quantify the machine surface in terms of maybe surface roughness or something?
Well, usually the process, it will be a part of the process. Process specifications will be provided
Okay.
to the airline. So this will be part of process specifications in the repair manual. What is to be done.
But you quantify the quality of the machine surface, like how?
Well, usually the way it will be done, okay, it will be saying, okay, 150 grit sandpaper, you sand it to smoothing, or like that. And that's it, usually.
Okay. Thank you.
Okay. Next one. Any other question from anyone? No? But I just want to have the comments. Did you find this presentation today interesting? Because I was talking about the many other various tests, which probably I'm not sure about, whether anybody has been involved in any testing or not.
Yes, sir. This was interesting actually, particularly the calculation or the measurement of the factors which we consider while arriving at allowables. So that was particularly very useful for us.
Yeah, if you are interested in reading about it, Mill Handbook 17, Volume 1.
Okay.
That.
Yeah. So these knockdown factors, what we should, apply to the B basis values mostly we use. So that, finally, how do we arrive at a design value for the analysis considering all these knockdown factors?
Yeah, that's right. So this is what I just provide only a summary, but if anybody is interested, you can always discuss with me in details. If you are trying to work out some design allowables or no parameters effect, I'm willing to help you anyway.
Okay, thank you.
Another question which I might like to put to Professor Dinesh if he's there.
Yes, I'm around, Dr. Gar. Please go ahead.
Yeah, just, let me just open that presentation. Question, AG question. Oh, what happened? Come on, there's a tray. Question and answers. Okay. I was just trying to show this structure last time, and on this screen, can you see the screen now?
Yes, I can. Yeah, please go ahead.
Okay. My question was, I don't know, you would have graduate students working on some projects, and I was just thinking if somebody was interested, it didn't take, just considering a real type of structure, some kind of a trailing edge box, to decide about the dimensions and looking into how the load diffusion occur from one part to another part. This region becomes quite complex, basically, but it gives a good feel for the structural engineers how really you would go about analyzing the real structure rather than just assuming a hypothetical beam or hypothetical shell analysis. Yeah.
True.
So it could be interesting to just consider in your design class, or somebody wants to work in a group for the real structure, just picking up some example and working out how the load diffusion occurred, then working out the sizes represented.
Sure, yeah. So are you saying that you have some specific data that you would like to share?
No, I don't have any data. This is
you're generally suggesting that we could find it in the open literature, any realistic structures, information like this to.
Well, realistic is, suppose this box, you can just consider dimension like a 150 millimeter. This could be almost like a 2 meters or 1 meter, just 1 meter, couple of ribs, and see with just 2 hinges. There's a simplistic assumption that only torsion, because this is like a torsion box.
Yeah.
This is actually structure. There's a flap around basically. 787. But I can't put any actual things. So I just made declaration. It's all hypothetical internal structure I'm putting.
Right.
So just assuming the dimensions, anything, just to consider a particular amount of torque you apply, how the box will behave. So box is nothing but this front spar, rear spar, and the trailing edge structure. So if somebody is interested, I could just provide the information, some more details. Roughly, I have to make it up, but it depends upon your interest of the students, and of course, the curriculum basically depends on the curriculum. I won't like to interfere with that at all.
Sure, yeah, I can explore if anybody is interested. If anybody right now who's in the audience, would you like to take that up? Otherwise, I can throw it up to the big group. Yeah, maybe we can get back to you on that, Dr.
Oh, that's okay. It depends upon your, what is the commitment of the students in the class, how many hours of work they can afford to have. So it's all. I was just thinking about it. It could be good, interesting as a practical project to your graduate students to work out the real structure in the aircraft design.
Because I think most of the students are already committed to having all of their time devoted to a particular research topic already. So maybe when we have a new student, maybe we can probably.
Yeah, that's okay. I was not thinking about that they should be disturbed from what they are doing already.
Sure.
So. Okay. Are there any other questions from anybody? Were you close today? No, I think
not. Yeah,
we can close today's lecture, and next week another thing. I think this chapter will be over next week. I'll finish.
I see. Okay.
These. Do you want me to continue and deliver the lecture as we said for the bolted joints?
Yes, I think that will be quite useful when you're looking at the analysis and design for both joints as well as the damage tolerance that we were.
Okay. All right. Yeah. I was thinking because already now you're giving me on how many lectures? We have completed 5 lectures.
This is the 5th, yeah.
So I was thinking about whether you have time or not for the students for these lectures.
We are quite flexible on that as long as you have
That's okay.
time available.
I can continue. No
Sure,
problem.
sure. Yeah.
Okay.
So we meet next this Thursday, right?
This Thursday, yes.
Yeah.
Same time.
Same time.
Okay.
Thank you
All
very
right.
much.
Good night. Good evening.
Thank you.
Take care. Bye-bye.